Next up, we want to look at a slightly more complicated pumping problem. Here we have a 10-meter tall conic tank with radius 3 meters is filled with water up to the 6-meter mark. How much work is required to pump out all of the water? So the only difference between this problem and the last problem is whether or not we have a conic or a cylindrical tank. So here we have a similar picture, but let's make this a little bit bigger. But we have this cone that is holding our water instead of the cylinder. So again, this thing is 10 meters tall. And again, this thing has radius 3 meters. And again, it's filled with water up to the 6-meter mark. So in order to think about how much work is going to be required to pump out all of the water, we're going to apply a similar approach that we did in the previous problem. We're going to look at a given layer of water, and we're going to ask how much work is required to pump out that layer of water. So again, we're going to want a frame of reference. So I'm going to think about the x-axis as being vertically oriented here. X equals 0 is again going to correspond to the top of the tank, and we're going to look at the layer of water associated with a arbitrary kind of x value here. So if we're looking at this layer of water, there are again kind of two questions that we need to answer. The first of which is how much water is there, and the second of which is how far is it from the top of the tank? How far do we need to move it? So the distance question is a little bit easier to answer here. So if we think about the distance, the thin kind of layer of water, distance layer of water has to travel. In order to get out of the tank is going to be x meters by kind of just construction of how we've set up our x-axis here. We need this layer to be pushed all the way up to the top of the tank, and well, it's x meters below, so got to move it up x meters. The question of how much water there is a little bit more challenging this time. So again, what we want to do is we want to look at the volume of water of kind of this thin layer that we're setting up here. So we've got this disk here again. Maybe we should draw it a little bit more disk-like. So we've got our disk of water here that we want to raise to the top. It has height dx. But the radius, whereas in the previous problem we knew that the radius was 3 because we were looking at a cylinder that always had a radius 3, here the radius of this thing, of this disk, changes depending on how x changes. Certainly at the very top, the radius of a disk that we'd be looking at would be 0, or would be 3, and at the very bottom, the radius of a disk that we would be looking at would be 0. And in the middle, it's somewhere in between those numbers 3 and 0. So we need to do a little bit of work in order to figure out what exactly the radius of this layer of water is. So we're going to draw a slightly more detailed picture here, where we're going to kind of slice this tank with a plane which includes the x-axis and also kind of passes through a diameter of this circle here. So what we get is, if we let me see if I can draw a good plane here. So the plane that I want to draw is going to pass through kind of this radius. So it's going to pass through the center of the top circle, and it's also going to include the x-axis that I've drawn here. So the plane that we're going to get is we're going to have kind of the top of the triangle in the top of our plane. We're going to have the two sides of the tank here represented this way. We know the water line is somewhere here, and the radius that we're interested in is kind of this purple distance here. So in other words, what I've got is I can again kind of draw this x-axis here. Here's x equals 0. Here's x equals 4, because we know it's filled to the 6 meter mark, so it's 4 meters from the top. This is my given x value here, and then at the very bottom we have 10. All right, so with this picture, maybe what we want to do, since we're interested in this radius, maybe the thing that we want to do here is draw kind of this center line. So this line makes a right angle with the top of the triangle, and it also is set up to divide this triangle, or this cross section of the cone, into two equal pieces. So with that, what we want to notice is this kind of purple triangle that I'm tracing out here is similar to this red triangle, where we remember that similar triangles means that they have 3 of the same angles, and we notice that the purple triangle and the red triangle both have right angles, and they also both share this angle here at the bottom. Since they share 2 angles, they have to share the third, and so these the purple triangle and the red triangle are similar. Now the quantity that we're trying to figure out here is maybe what we would call the radius of this circle or of this layer of water that we started with, which corresponds to the length of this horizontal line in this triangular picture here. Now, some other quantities that we know here are that the side length here at the top of the triangle is 3, which corresponds to the radius of the cone. We know that the height of this red triangle is 10, because that's how tall the cone is. And we also know that the distance from the top of the triangle to this horizontal purple line is x. So with all of that in mind, we want to apply some of the ratios here, and we are going to actually need to then notice that the distance that we're really interested in here is a side length on this bottom triangle. We want to know what this vertical side length on the bottom triangle is, or the purple triangle, and since we're going x meters from the top of the tank to this purple line, the number of meters from the purple line to the bottom of the tank has to be 10 minus x. All right, things are getting a little bit messy here, but this bottom length here is going to be 10 minus x. Great. So maybe let's draw those triangles in a little bit neater of a fashion. So we have the red triangle here, which looks something like this. It has dimensions 3 and 10. And the purple triangle, which is similar, has dimensions r and 10 minus x. So when we're working with similar triangles, what we can do is we can take ratios of the corresponding sides. So what I find here is that the ratio of r over 3 has to be equal to the ratio of, so let's see, so we took purple side over corresponding red side, has to be purple side over corresponding red side. So that's going to be equal to 10 minus x over 10. And fortunately enough, this is going to tell me that r is equal to 10 minus x over 10 times 3. All right, so what was the point of doing all of this? Well, the point was to talk about how much water was in a given layer. And we know that the amount of water in a given layer, so let's see, so what are we looking for? We're looking for the force due to gravity. That's right, the weight of the water. So the weight of the water in layer X is given by pi times the radius of that layer squared times dx. So this is the volume of the water in meters cubed. And if we multiply by that 9,800 number, which tells us the number of newtons that the water weighs per cubic meter, this is going to give us the weight of the water. But we have a problem with kind of this statement here, and maybe I should have started by writing this out, which is that we have the variable r here. R depends on x, and we have the quantity dx here. We would really like to integrate with respect to x, and so we need to get rid of this r and exchange it for something in terms of x. And that's the point of setting up this equation, which tells us exactly what r is in terms of x. So now that we've, I guess, done this work, we can go ahead and replace it. So this is 9800 times pi times, let's simplify this r formula a little bit here. We can write this as 3 minus 3x over 10. So this is 3 minus 3x over 10 squared. All right, so we have the weight of the water in layer X. We have the distance that that water has to travel. And so what we have to do now is we have to add up all of the, so I guess to get the work for a given layer, the work for layer X is going to be the product of the distance that it has to travel and how much it weighs. So this is going to be 9800 times pi times this 3 minus 3x out of 10 squared times x. So here we have weight times distance. Great. All right, so now what we have to do is we have to add up all of the works that it takes to move a given layer out of the cone, and we have to then, we have to add up all of those works, which looks like integrating this thing right here. So let's write that down. So the total work is going to be the integral. Here my smallest x value for the top layer of water here corresponds to x equals 4. So I'm integrating from 4 up to the largest x value, which is at the bottom of the tank here, and that is x equals 10. I'm integrating 9800 pi times 3 minus 3x over 10 squared times x dx. All right, so we have a little bit of work to do here before we can integrate. Let's see, I think I'm going to expand out, well, let's factor out this 9800 pi. And let's expand out the 3 minus 3x over 10 squared into 9 minus twice the product of the terms. So 2 times 9 is 18 out of 10 is going to give me 9 out of 5x plus 9x out of 100, 9x squared out of 100, x dx. And then we can factor out a 9 and also distribute in that x. So that's going to give me 9800 times 9 times pi, integral from 4 to 10 of, let's see, we're going to have an x. We're going to have a minus x squared over 5. And we are going to have a plus x cubed out of 100. All right, great. So the last thing to do is to actually integrate and evaluate. So we have 9800 times 9 pi times x squared over 2 minus x cubed over 15 plus x to the 4 out of 400. And we are evaluating from 4 to 10. And if you do that, you're going to get approximately 1.1 times 10 to the 6 joules. So notice here that we're getting a difference between the answer of this problem and the last problem, about a factor of 10. So the fact that we have this cone here that isn't all the way full, just like the last one, is really affecting the amount of work that it takes to empty it out because, well, there's much less water in part. So we get kind of less work here that's required to empty this tank. All right, I think that's it for pumping problems. In the next part of this section, we're going to take a look at hydrostatic pressure and force.